Let's do the Unit 5 progress check for response questions, Part B for BC Calculus. And here is the very first question. Again, the stuff that they put at the very beginning is to show all your work and the domain, blah, blah, blah. Here goes. The graph of the continuous function g is shown above for -3 to 5. The function g is twice differentiable except at x equals 1. Stuff that is good to know. Notice you do not have an equation. Do not assume an equation. Don't do that. You have all you need. They told you what you need. Now f, different function, is the function f of 1 equals 3, and the derivative is given like that. Okay, well, that works. We can do that. So let us jump in with part A. Find the x-coordinate of each critical point of f. Critical points occur where the derivative is equal to 0 or the derivative does not exist. The derivative does exist. We're going to classify each critical point as the location of a relative minimum, maximum, or neither, because just because the derivative equals 0 doesn't mean that we have a critical point. So let's do it. By the way, let me kind of follow up with what I just said. Scrap paper. Maximums and minimums occur where the derivative equals 0. Look, maximum, minimums, there. Or here, this is not a maximum or minimum, but that is where the derivative equals 0. So this is maximum, minimum, neither. So not only do we have to have the derivative equal to 0 or not exist, we also have to have a change of sign of the derivative. And in this case, the function is going from increasing to increasing. So no change of sign of the derivative there. All right, random thoughts out of the way. Let's move on. Number 1, part A deals with f of x, and they told me what f prime of x was. It was 6x squared minus 5x times e to the x. There's that. And we are going to find where this thing equals 0. Here we go. What about this f of 1 equals 3? Not good to know. I mean, you don't need to know it. I'm sorry. Just not helpful at all. Not yet. Maybe one day. We're going to solve this, so let's start factoring. First of all, there's an e to the x that's factored out for us already. Very fortunate for us. Also, there's the greatest common factor of x. We'll factor that out. 6x minus 5 times e to the x equals 0. We're going to set each factor equal to 0. You know how this works. X equals 0. 6x minus 5 equals 0. E to the x equals 0. Oh, wait. No, it doesn't. That was a waste of time. E to the x will never equal 0. There's a horizontal asymptote on the x-axis for this graph. So x equals 0 and 5 over 6. This is calculator inactive, so we're going to have to do this without a calculator, but trust me, it is super easy. Trust me. We want to figure out what happens, or where the critical numbers are, what happens at each of these points. So let's draw our number line. The domain is all real numbers, so we are going to go from -infinity to infinity. This is what we call sign analysis, because we're analyzing our signs. Now, I'm going to say a lot of things that I don't write, because I'm going to do this in my head, but I think it's very logical to do it this way. So let's pick a number. Let's start here. Let's pick a number that is negative, a number less than 0. If I plug a negative number in for every x here, I want to know what I get. Okay, I have a negative, and then I plug in a negative here, and I have 6 times negative minus 5. So I have a negative times a negative, and then I have a negative that goes here. Well, e to a negative is just 1 over e to whatever power. Right? So just again, here's what happens in my head. Grabbing some more scrap paper, scrap paper actually. If I had e to the negative, I don't know, 10, that's really 1 over e to the 10. That's still positive. Ridiculously small, but still positive. So we have negative times a negative times a positive. That tells me that the derivative is positive. Negative times positive is positive. So we are determining the intervals of increase or decrease, which will tell me if these are maximums or minimums, or neither. Okay, let's plug a number in here that falls between 0 and 5 over 6. Can't use a calculator. I'm going to go for something slightly obvious. 1/6. Okay, plugging in a positive 1/6. Positive goes here if you have a positive. Positive 1/6 goes here. If I plug the 1/6 here, I would have 6 times a 6th. That's 1. 1 minus 5 is negative. Okay, positive times a negative times, plug in a positive, you're still going to get a positive. So positive, positive, that must be negative. Okay, and then we'll plug in a number over here. Any number will do. A number larger than 5 over 6, there's an obvious. Let's go for 1. Plug in a 1, you get a positive. Plug in a 1, you get a positive. Plug in a 1, you get a positive. So we have a positive. So this one and this one are both critical numbers because that is where the sign of the derivative changes. So the sign of the derivative changes at 0 from positive to negative, and the sign of the derivative changes from negative to positive at x equals 5/6. Let's write that down because they did say justify your answers. So here goes. There is a maximum at x equals 0 because the derivative changes from positive to negative at that point. Okay, similarly, there is a minimum at x equals 5/6 because the derivative changes from negative to positive. Okay, let's make sure we've answered everything. Find the x-coordinate of each critical point. Done. Now, notice they said find the x-coordinate. They did not say find the maximum value, find the minimum value. If they would have done that, then I would have had to go a little bit further and actually plug it into the function, which I don't have, so wouldn't be able to do that. But I do know the maximums and minimumness of it. Let me zoom in just a little bit. There we go. All right. Part B. Find all values of x at which the graph of f has a point of inflection. Give reasons for your answers. Okay, points of inflection occur where the second derivative changes signs. That's where the second derivative equals 0 or does not exist. The does not exist thing is not going to happen in this particular problem. So I need a second derivative. All right, here goes. Well, in order to get a second derivative, I need a first derivative. I don't recommend that you do what I'm about to do. It's a waste of time on the AP test, but I'm going to rewrite the first derivative. Otherwise, I'll just be doing this the whole time, okay? So I just need to point at it a lot. So I find it beneficial to do this. Okay, so there's that. I need the second derivative. I hope you realize what needs to happen here. I need the product rule, which would be f prime g. Stop right there. Do not leave it like that. That is wrong. F prime g. All right, good, good. Now we're on the same page. Plus f g prime. It is its own derivative. And we're going to set this equal to 0. What in the world are we going to do with that? Now, you could waste your time, and it is a perfectly valid strategy, but you could waste your time by distributing e to the x, but then in the end, you'd realize that I'm just going to factor it out anyway. So there is a greatest common factor here of e to the x, and therefore, we're going to have 12x minus 5 plus, and it's plus because of that plus, 6x squared minus 5x, and that's equal to 0, and we're going to keep solving that. So e to the x, and let's put this in a nice, neat quadratic standard form order. 12 minus 5, 7x, and then minus 5. Yes, it factors. If it doesn't factor, we'd have to use the quadratic formula, but we'd still deal with it. This is calculator inactive, though, so no cheating. All right, let's do it. We're going to keep factoring e to the x, which, by the way, we'll get no answers from there. E to the x will never equal 0, no matter how hard you try. This one does factor. I usually use trial and error, but I've got ink pens going on now, so I'm not going to. Two numbers multiply to give me 5. We're limited on our options there, so we'll start there. We also have x's involved, so 6 must be 6 times 1 or 2 times 3. If I do 2 times 3, thinking ahead here, I'll have 10 and 3. 10 minus 3 gives me the 7 that I want. My signs have to be different to get this negative 5 anyway, so 10, and there's that. Okay, so I would love to waste your time by saying e to the x equals 0. It doesn't. We've established that can't happen, but I also know that 3x plus 5 equals 0, so x is negative 5/3. And x is also where this equals 0, where this factor equals 0, so it's 1/2. So we're going to do a similar sign analysis for this one to make sure that they are indeed points of inflection. Now, the question did not say when does it change from concave up to concave down or anything like that. It just said, does it have a point of inflection? And the answer would be no if on one of these intervals that we're about to draw, if on one of these intervals we transitioned from negative to negative. In other words, the second derivative was negative, then the second derivative was negative, which means concave down to concave down. That's not a point of inflection, okay? That's a point of expectancy with delayed gratification. That's not gonna happen. So again, same idea gonna happen here. Let's go for something super negative. Something super negative over here, negative big, okay? Just negative big. We're doing this in our head. Negative big goes here, you still have a positive. Negative big goes here, you have a negative. Negative big goes here, you have a negative. Because I have positive times negative, I have a positive. So the second derivative is positive. I recommend that you plug these into the factored form. Now, there is a slight exception to that. And I want to just pause this lesson for just a second and address that slight exception. I do recommend you plug things into the factored form, but if you ever have a factored form that's like this, I'm just making this up, and you're like, man, I really don't like that negative in the front, and you just divide it out, you have just changed every sign of what you're going to do when you do your number line, okay? So go back to the original factored form before you divide out constants, particularly negatives. I mean, positive constants, not going to change your signs, but it's a bad habit to have anyway. All right, let's plug in a 0. If I plug in a 0, I'd have e to the 0. That's 1. So positive, plug in a 0, get a positive. Plug in a 0, get a positive. Really? Okay, sounds interesting to me. So I believe that we are going to have a, wait a minute. I'm looking back at my work. Something feels wrong about this. No, I plug that in and I get a negative. Okay, yeah. Whoa. Sorry, all right. Plug in a 0, get a positive. Plug in a 0, get a positive. Plug in a 0, get a negative. All right, spoke too soon, wasn't thinking clearly enough, was going too fast. Sorry about that. All right, plug in a positive, big positive, well, something bigger than a half, so like 1 will do. Plug in a 1, you get positive. Plug in a 1, you get positive. Plug in a 1, you get positive. No choice but to be positive there. Can't mess that one up. So we have points of inflection here and here because the sign of the second derivative changes at both of them. And it said give reasons for your answers. So here we go. And again, making sure I'm reading it correctly. Find all values of x at which the graph of f has a point of inflection. Okay. I'm about to list x values, and I want to tell why I know that. And I've shown some work here that demonstrates it too. So we're in good shape. There are points of inflection at x equals negative 5/3 and x equals positive 1/2 because the second derivative changes signs. You could say there. I'm going to get a little more specific at these or those x values. Okay. That brings us to the end of part B. Let's move on to part C, which is a little bit tricky. So far, we've dealt with the function f, which they gave us the derivative of and a point for. But now they're going to deal with, well, g. So here goes. Here's g. This is part C. Find them too. Find them so you can fill them in. Fill in the missing entries in the table below to describe the behavior of g prime and g double prime on the interval from -3 to 5. Indicate positive or negative. All I have to do is write positive or negative, give reasons for your answers. So I have this in 2 separate pages so we can kind of talk about it. I want to know the positivity or negativity of the derivative of g. Wait, pause. What's g? It's the graph. Okay, looking at the graph. I want to know the positivity or negativity of the derivative of g for the x values from -3 to +1. So let's look at it. All right. Is the derivative of g positive or negative from -3 to +1? Okay, the graph is decreasing, so that gives it away right there. So I am going to go ahead and start writing my answer. I'm not going to write it in here, fill in the missing entries in the table below. I'm not going to do that. I'm just going to write a few little words down. So g prime of x is negative for negative 3 to x to 1, and I'm gonna stop there. I do want to give a reason, but in order to be a little more concise, I am going to just move on a little bit. You'll see where this is going. If you want to go ahead and give your reason, you can. And the reason is this. The reason that the derivative is negative is because the function is decreasing, but I'm not going to write it yet. Because when I get to this next piece, I want to know what the derivative is doing, or the sign of the derivative, from 1 to 5. Well, from 1 to 5, it's also decreasing. So I'm going to kill two birds with one stone. Not literally, that's cruel. But I'm going to say it's negative for that and for that. And now I'll give a reason for both. Same reason for both. Because G is decreasing on these or those intervals. Okay, so we have filled in the chart for the G prime. Now let's fill in the derivative or the chart for G double prime. So the second derivative from negative 3 to 1. Second derivative from negative 3 to 1. Okay, second derivative deals with concavity. We have concave down. Sounds negative to me. And let's look ahead. Concave up, positive. Okay, we're going to write that down. The second derivative is negative for the interval from negative 3 to positive 1 because g of x is concave down on this interval. And one more sentence. You know what's about to happen. The second derivative is positive for 1 to 5 because, oops, I forgot how to write, no, because g of x is concave up on this interval. Okay, that is part C. Alrighty, let us move on. Part D asks us to do something wild and crazy. They said, I'm reading it and you can't see it yet, but they said let h be this function, f of x, g of x. And then they said, is h increasing or decreasing on the interval from 1 to 5? I'm going to write it out so I can point to it and just kind of use it as a reference. So is h of x, you don't have to rewrite the question on your free response, but I'm doing that for the sake of explanation so I can just kind of, well, explain. Is h of x increasing or decreasing on the interval from 1 to 5? And then give a reason for your answer. And so first of all, I know increase or decrease based on derivative. So let's find the derivative. Now, if you're looking at this and you're like, well, wait a minute, I have f. I don't even know f. They didn't tell me f. They told me the derivative of f. So that's all I know other than that one dot right there at one point. And then g is just a graph. How am I going to... Don't panic about how you're going to do it. Just jump in with what you know, for real. That is a very effective strategy. Is it increasing or decreasing? I better find the derivative. We'll go from there. You can get points for just finding this sometimes. Sometimes. Depends on the context. Okay. Is the function increasing or decreasing? Here's what I want to know. Is this positive or negative for these values? So I would love to plug in values and figure it out, but I don't have that luxury. But here's what I'm going to do, and I'm going to just kind of articulate what I'm thinking in this way. So for 1 to 5, f prime of x is something. I'm doing them in order. G of x is something. F of x is something, and g prime of x is something. I'm thinking signs here. All I care about is signs. I don't care about numbers. I just need signs. So I'm going to go ahead and go for the obvious ones. Like I can get the g stuff pretty easily because I've got a graph to look at. So g from 1 to 5 is negative. Okay, g is negative. All right, good to know. G prime is, well, the derivative of this, well, it's decreasing, so it's, well, negative. So there we go. We've got part of it so far. From 1 to 5, the derivative, wait, I can do this. I can do this because I have the equation of the derivative. So if I plugged in any number from 1 to 5, if I plugged in any number from 1 and up, then I'm going to get a positive number here. That's going to happen. And we actually already figured this out. So here's the deal. My derivative is positive for f for all x values greater than 5 over 6. So from 1 and up, we're definitely good. So we have already justified that here. Let's just go ahead and write that. And now we're to the hard part. We're to this part where I can't really say much about what happens in the original function because they didn't tell me much. But wait. And I need to justify this. I don't need to justify that or that. I've already justified that in part C. I already justified that in part A. Okay, so you don't have to be like, well, I did this sign analysis and I found the first derivative to equal 5 over 6 and look what I did here, and you did it. You did it. Okay, you're good. You're fine. But what about this guy? Is he positive? Is he negative? I don't know. And where am I going with this whole thing? So here's the deal. If we have positive times positive plus positive times positive, we have a positive, and this function is increasing. If we have negative times negative plus negative times negative, we have a positive, and this function's increasing. But if both of these are different and both of these are different, we have a negative plus a negative, so we have a negative and the function's decreasing. That's where this is going, okay? This is really good to know. So I don't know about this, but here's what I know. And this is where we use that one piece of information that we've never used. They told me what happens at f of 1. It's 3, okay? I know the function is positive at 1, and check this out. I know the function increases from there. This function will never be negative from 1 and forward. Therefore, this is positive. If that didn't go through your head, now you get one more strategy to where maybe it will. Okay, I want to justify that. Again, justified. We've beat the crap out of those we've done that in the other sections. But this one, because f of 1 is 3, which is positive. I'm going to just throw that in just for fun. And f prime of x is positive for all x is greater than 1. I could say 1, but 5 over 6 works as well because 5 over 6 backs it up even further, so we're definitely positive. So we have justified that. Now, here's what's about to happen. And this is not incorrect. This is just me cranking out some ideas. So h prime of x equals positive times a negative plus positive times a negative, which gives me a negative. And therefore, h of x, and this is a good explanation, and so is this. H of x is decreasing on the interval from 1 to 5. One more random thought that I want to say. All the stuff that I put here, I think it's important that we don't just put it here. We need to put it in context. This does not apply for any section, any interval, other than 1 to 5. So we need to clarify that we are dealing with the interval from 1 to 5 for this right here. There you go.